Hi, Jamerson Tutorials for Further Mathematics. In this question, a particle P of unit mass moves on a curve with polar equation r equals a sine theta under the action of a force of magnitude f of r, which is always directed towards the pole O. Show that a r squared theta dot equals h, where h is a constant. B r dot squared equals h squared all over r to the fourth into a squared minus r squared. C r dot dot equals h squared all over r to the fifth into r squared minus 2a squared. D f of r equals 2a squared h squared all over r to the fifth. Roman 2, a particle P moves in a plane so that at time t seconds, its polar coordinates r theta are given by the equation r equals at squared, theta equals 1/3 t cubed, where a is a constant. Show that the speed of P when t equals 2 is 4a root of 17. That was Further Mathematics, Paper 3 of GCE, June 2008. Going back to the question first, there are some key phrases there or terms that we need to highlight. The first one is unit mass. So a mass of one unit. It's moving on a curve with polar equation r equals a sine theta under the action of a force of magnitude f of r, which is always directed towards the pole. So those are the key parts of the question. If we have to start with the first part, we have to prove that r squared theta dot equals h, a constant. And in order to handle that part, we'll first look at what is happening. This is the pole, and there is the curve that the particle is moving on, particle P. So we have radial motion. There is an acceleration along OP, which is called the radial acceleration, and there is also a transverse acceleration which is perpendicular to the radial one, and we call it the transverse component of the acceleration. If the particle moves in such a way that the force is acting towards the pole, then motion has been restricted. Remember, this is motion in 2 dimensions. This is the topic, radial and transverse motion, which is simply motion in 2 dimensions. And in this case, the force is acting towards the center, so the motion has been restricted to the radial one only, and so the transverse acceleration will be 0. Motion is only in this direction, so the component in the transverse direction becomes 0, and that is the base of our solution to the A part of the question. So I go to A. We need to say, since motion is purely radial, A transverse equals 0. Now, from the formula booklet, there are 2 formulae for A transverse. You have r theta dot dot plus 2r dot theta dot. Another variant of it is 1 all over r d over dt of r squared theta dot. so equals 0. This one is an equivalent of this. If you differentiate this expression in the bracket with respect to t and divide the result by r, you get back this one. So they're equivalents. And for me to do this proof, r squared theta dot equals h, the second formula seems appropriate because actually the left hand side of the proof is this expression in that formula, and so I will use but this other option and allow this one. So I get d over dt of r squared theta dot equals 0. I've simply multiplied through by r, and this is a differential equation which I need to solve in order to obtain this expression which is in my proof. So I cross multiply, I get d of r squared theta dot should be equal to 0 dt. And in order to get r squared theta dot, I need to remove the d, which is indicating differentiation. So you remove differentiation by reversing the process with integration. So I integrate both sides. I'll get that integral of d of r squared theta dot should be equal to integral of 0 dt. And integral reverses the d, so you're just left with r squared theta dot equals the integral of 0 is 0 plus my constant of integration. Therefore r squared theta dot equals h. The question we're told to prove that r squared theta dot equals h, which is a constant. So the h is the constant in this our case here, and that is already the proof as required. Okay, in the B part we are asked to prove that r dot squared equals h squared all over r to the fourth into a squared minus r squared. So in order to have r dot first, I have to look at the parts I have proven already or in the question itself to see what I can do. R dot, remember, is the r dt. There is r here, but it is squared. If I have to differentiate this to arrive r dot, I could have complications, especially the fact that I will have theta dot dot. So I prefer to go back to the equation and look at the equation of the curve. It is easier to handle while differentiating. So we're going to start from there. In the B part, we start with r equals a sine theta, which is the equation of the curve. And if I differentiate both sides with respect to t, I will have that. Now, there is something here that we need to do. We are differentiating with respect to t, but the expression varies with theta instead. So there is a sine theta there. There is no t to differentiate. So we are bound to use the chain rule. We first take d over d theta of that expression and then multiply by d theta dt. That is how we'll get d over dt of a sine theta. And when you differentiate that, you get a cos theta into d theta dt is theta dot. and the r dt is r dot, so we can say that therefore r dot equals this. Remember, we are to prove that r dot squared equals something, so we have to square both sides in order to see how the proof is approached. R dot squared should be equal to a squared cos squared theta, theta dot squared. From the proof in A, theta dot can be made the subject and substitute here. Remember again, when you have a proof like this, you have to look at the proof from time to time to see what is required. The proof has only H, R, and A, so any other thing has to be eliminated. And so we would need to eliminate cos squared theta and theta dot squared in order to approach the proof. So from the A part, we can make theta dot the subject, but r squared theta dot equals H implies theta dot equals H all over r squared, and theta dot squared should then be H squared all over r to the fourth. I also need to remove cos squared theta, and the equation of the curve can provide me something useful. We have cos squared theta plus sin squared theta, which always gives 1. That's a Pythagorean identity, so we could square both sides of that polar equation of the curve. R squared equals a squared sin squared theta, which could also be a squared into, so sin squared theta from the Pythagorean identity, as I already said, should be 1 minus cos squared theta, and that gives us a squared minus a squared cos squared theta. That is my r squared. The expression a squared cos squared theta is already in a statement that I am struggling to improve and get the proof. So I will simply make a squared cos squared theta the subject here, which should be a squared cos squared theta. If I send it this way, it will become positive. Then I maintain a squared and send r squared the other way, so negative r squared. And so I have replacements already for a squared cos squared theta, which is here, and then theta dot squared. So I can now say therefore r dot squared equals a squared cos squared theta is a squared minus r squared, and theta dot squared is h squared all over r to the fourth, and r dot squared should then be h squared all over r to the fourth into a squared minus r squared as required. Now in the C part, we have r dot dot equals h squared all over r to the fifth into r squared minus 2a squared. Again, r dot dot is the differential of r dot with respect to t. So if I go to the B part and differentiate both sides with respect to t, I would surely have that proof. It is more appropriate since it also contains the very constants and the variable r, which are in this other proof for r dot dot. And so I'll begin with this and then differentiate to arrive the proof in C. So C from r dot squared equals h squared all over r to the fourth a squared minus r squared d over dt of r dot squared equals d over dt of h squared all over r to the fourth into a squared minus r squared. And differentiating r dot squared with respect to t, I am supposed to use the power rule. So I'm differentiating a function which is raised to a power. The function I'm differentiating is r dot, so I first bring down the power, subtract 1, then differentiate the function. That gives 2 r dot, then the differential of r dot again, which is r dot dot with respect to t, so it should give r dot dot. Then so it is the differential of r dot squared, which is 2r dot, then the differential of r dot with respect to t, we should give r dot dot, equals d over dt of, I would modify this expression so that it is in the form that I can easily differentiate, which gives h squared a squared r to the negative 4 minus h squared r to the negative 2. So when you expand, there's r squared divided by r to the fourth, which should give r to the negative 2. And again, in this part here, you have to be very careful. We are differentiating with respect to t, but the expression that I'm supposed to differentiate does not have the variable t. Instead, the variable that is there is r. Remember, h and a are constants. So I would again apply the chain rule by first differentiating with respect to r and then multiplying the result by dr dt. That is the chain rule. So differentiating with respect to r first, I will get negative 4h squared a squared r to the negative 5 minus 2h squared r to the negative 3. All that dr dt multiplied. The chain rule. From there we simplify to have 2r dot dot equals negative 4h squared a squared all over r to the fifth, minus will be plus 2h squared all over r cube, all that r dot, dr dt is r dot. R dot cancels on both sides and 2 also cancels, and so we should be talking of r dot dot equals, I can find the LCM, which is r to the fifth divided by r to the fifth. That will give us negative 2h squared a squared plus r to the fifth divided by r cube will be r squared times h squared will be h squared r squared. Therefore, r dot dot equals, h squared is common at the numerator, so we write h squared all over r to the fifth, which is common at the denominator, into r squared minus 2a squared. So that is the proof there that we're required to do for the C part. And now the D part says f of r equals 2a squared h squared all over r to the fifth. Remember again, the question says the motion is always directed towards the pole. And so this motion is along PO in the opposite direction to the acceleration in that direction, which is the radial component of the acceleration. So it implies that we have to use Newton's second law of motion. In the D part, F of R, the force, should be equal to the mass, but the force is negative because it is moving towards the particle. The force is directed towards the pole, meanwhile the acceleration is away from the pole. So it's a negative force, ma, and the a here is the radial component only, because the transverse component of the acceleration is 0, as already explained in the previous part of the question. The particle was said to have unit mass, so we just have negative AR. And from the formula booklet, the radial component of the acceleration is given by r dot dot minus r squared theta dot, minus r theta dot squared. R theta dot squared. That is the formula. When you expand the negative sign, you get r theta dot squared minus r dot dot. Now, from the previous parts, we already had theta dot squared. This is it here. So I would proceed to replace it. R into h squared all over r to the fourth minus r dot dot. Again, we are just from proving it in the C part. This is the expression for it. So I will replace it to h squared all over r to the fifth into r squared minus 2a squared. And when I expand to simplify, I get h squared all over r cubed minus h squared over r to the fifth times r squared will be h squared over r cubed. Negative times negative becomes positive 2a squared h squared. And therefore, f of r equals h squared on r cubed minus h squared on r cubed would cancel, and you are just left with 2a squared h squared all over r to the fifth as required. So this is the D part proven. Now for Roman 2, a particle P moves in a plane so that at time t seconds its polar coordinates r theta are given by the equation r equals a t squared, theta equals 1/3 t cubed, where a is a constant. Show that the speed of P when t equals 2 is 4a root 17. So we begin with Roman 2. First of all, the speed of the particle is supposed to be the magnitude of the velocity. And the velocity has two components, the radial component and the transverse component. radial component of the velocity, again from the formula booklet, is given by r dot, and the transverse component is given by r theta dot. So we bring in the equations that were given. R is at squared. We say, but r equals at squared implies that r dot, so r is already in terms of t. The r dt, which is r dot, can easily be obtained by differentiating the right hand side with respect to t, which gives 280. And when t equal to, r dot should be 2a into 2, which is 4a. So that gives us VR being 4a. Now, we are also given that theta dot equals, theta, we get theta first. Theta is 1/3 t cube, and that implies that theta dot, again differentiating theta with respect to t, would give theta dot. On the right hand side, I simply get 1/3 dot 3 t squared, which gives t squared. And when t equals 2, theta dot would be 2 squared, which is 4. Therefore, Vt, which is r theta dot, should be 80 squared for r into theta dot, which is 4. That gives 4a t squared. And when t equal 2 again, Vt would be 4a into 2 squared, which is 16a. Therefore, speed should be equal to the square root of, remember again what we said, the speed is the magnitude of the velocity. So we have to square the radial component, add to the square of the transverse component to get the speed. And the radial component was 4a. So I put 4a all squared plus the transverse component 16a all squared. This gives square root of 16a squared plus 16a squared into 16. We have square root of 16a squared is common into, when you divide 16a squared by 16a squared, you get 1, plus when you divide 16a squared into 16 by 16a squared, you get 16. And that gives us the square root of 16a squared into 17. The square root of 16a squared is 4a, so I send 4a out, and then we are left with root 17 inside. And that gives the proof as required. We were asked to prove that the speed when t equals 2 is 4a root 17.